When people first encounter quantum mechanics, one of the most disturbing claims they hear is that observation changes the phenomenon being observed. This sounds mystical, almost magical, as if conscious awareness has some special power over physical reality. I have spent much of my career trying to clarify what this really means, because the truth is both more subtle and more profound than the popular formulations suggest. Observation does change the phenomenon, but not because of anything to do with consciousness or human awareness. It changes the phenomenon because observation is a physical interaction, and in quantum mechanics, the distinction between the observed system and the observing apparatus cannot be drawn in the same way as in classical physics. Let me take you through this carefully, because understanding why observation changes the phenomenon is essential for understanding quantum mechanics itself. I should begin by explaining what we mean by observation in physics. In everyday language, observation suggests someone looking at something, a conscious being perceiving an object. But in physics, observation means something more specific and more technical. It means an interaction between a system we are investigating and a measuring apparatus that records information about that system in a way that can be read out and communicated. The key is that this interaction must create a permanent, macroscopic record that can be shared and verified. Whether any human being is present to witness this record is irrelevant. The observation happens when the interaction occurs and the record is created, not when someone later reads that record. Now, in classical physics, we assume that observation can be made arbitrarily gentle and non-disturbing. If we want to measure the position of a billiard ball, we can shine light on it and observe the reflected light without significantly affecting the ball's motion. We can imagine, at least in principle, making our measurements so delicate that the disturbance becomes negligible. Even if perfect non-disturbance is impossible in practice, we can always account for whatever disturbance we introduce and subtract it from our results to determine what the system was like before we observed it. In classical physics, the phenomenon exists in a definite state independent of observation, and our job is simply to reveal that pre-existing state as accurately as possible. Quantum mechanics tells us this picture is fundamentally wrong at atomic scales. The reason is not just that our measurements are clumsy or that we cannot make them gentle enough. The reason is that quantum systems do not exist in definite states until an observation brings definite properties into existence. Let me explain what I mean by this through a concrete example. Consider an electron. In classical physics, we would assume the electron has a definite position and a definite momentum at every moment, whether we measure these quantities or not. Our measurements might disturb the electron, but the disturbance is in principle calculable and correctable. The electron's position and momentum exist independent of observation. But quantum mechanics says something entirely different. An electron is described by a wave function, a mathematical object that encodes probabilities for different possible measurement outcomes. The wave function can be a superposition of many different position states, meaning the electron does not have a definite position before we measure it. It exists in a state where position is fundamentally indefinite. When we perform a measurement of the electron's position, something remarkable happens. The wave function, which was spread out over a region of space, suddenly collapses to a very localized state centered on the measured position. This collapse is not a gradual process that we can observe happening. It is instantaneous and discontinuous. Before the measurement, the electron was in a superposition of many positions. After the measurement, it has a definite position. The observation has not revealed a pre-existing position that we previously did not know. It has created a definite position from quantum indefiniteness. This is why observation changes the phenomenon in quantum mechanics. The phenomenon before observation is a quantum superposition. The phenomenon after observation is a definite classical outcome. These are qualitatively different kinds of things. The observation does not merely reveal what was already there. It transforms the quantum into the classical, the indefinite into the definite, the potential into the actual. But why does this happen? Why should observation have this special power? This question troubled me for many years, and I came to realize that the answer lies in understanding what we mean by a quantum system and what we mean by a measuring apparatus. In quantum mechanics, we must maintain a distinction between the system being observed, which we describe quantum mechanically using wave functions and superpositions, and the measuring apparatus, which we describe classically using definite properties and outcomes. The measuring apparatus must be described classically because we need to communicate our results using ordinary language and classical concepts. When I perform an experiment, I must be able to say that the pointer pointed to this mark on the scale, that the detector clicked at this time, that the photographic plate shows a spot at this location. These are classical statements about definite outcomes. If everything were described quantum mechanically, including the measuring apparatus, we would have nothing but wave functions and superpositions, and we could never actually report any definite results. Physics would lose its empirical content. So observation changes the phenomenon because it creates an interaction between a quantum system, described by a wave function in superposition, and a classical measuring apparatus that can only record definite outcomes. This interaction forces the quantum system to choose one of its many possible states, to collapse from superposition to a definite classical state that can be recorded by the apparatus. The observation is the process of this quantum to classical transition. Let me give you the most famous example of how observation changes the phenomenon, the double-slit experiment. When we send electrons one at a time toward a barrier with two narrow slits, and we do not observe which slit each electron goes through, we find that the electrons build up an interference pattern on a screen behind the barrier. This interference pattern can only be explained if each electron passes through both slits simultaneously, existing in a superposition of going left and going right, with these two components of the wave function interfering with each other. But now suppose we place detectors at the slits to observe which slit each electron passes through. When we do this, the interference pattern disappears completely. Instead, we get two simple bands on the screen, exactly what we would expect if each electron went through one slit or the other like a classical particle. The observation of which slit the electron goes through has fundamentally changed the phenomenon. Without observation, the electron is in a superposition and shows interference. With observation, the electron is in a definite state, having gone through one slit or the other, and shows no interference. This is not because the detectors physically bump the electrons and knock them off course. We can make the detection process as gentle as we like, using minimal interaction, and the effect remains. The interference disappears not because of crude mechanical disturbance, but because the observation forces the electron to have a definite path. Once the electron has been observed to go through a particular slit, it is no longer in a superposition of both paths, and without that superposition, there can be no interference. The phenomenon without observation is wave-like, showing interference. The phenomenon with observation is particle-like, showing no interference. These are different phenomena, and the difference is created by whether we observe the electron's path. Observation does not merely reveal what was happening all along. It determines what kind of phenomenon occurs. Werner Heisenberg, working with me in Copenhagen, discovered his uncertainty principle in 1927, and this principle gives a precise mathematical expression to how observation changes the phenomenon. The principle states that certain pairs of physical quantities, like position and momentum, cannot both be measured with arbitrary precision simultaneously. The more precisely we measure one, the less precisely we can know the other. But this is not merely a statement about measurement disturbance. It is a statement about what can exist. If we measure an electron's position very precisely, we force it into a state where position is well defined. But the act of forcing it into this state necessarily makes its momentum highly uncertain. Not because we have disturbed the momentum through the measurement process, though that happens too, but because a quantum state with well-defined position mathematically must have poorly defined momentum. The wave function for a well-localized particle is a superposition of many different momentum states. Position and momentum are complementary properties that cannot both be definite simultaneously. So when we choose to observe position, we change the phenomenon from one where position might have been indefinite to one where position is definite and momentum is correspondingly indefinite. When we choose to observe momentum instead, we change the phenomenon in the opposite way. The choice of what to observe determines what kind of phenomenon we will see. This is what I called complementarity. Different experimental arrangements revealed different complementary aspects of quantum systems, and these aspects cannot be observed simultaneously because the experimental arrangements needed to observe them are mutually exclusive. But both aspects are necessary for a complete description of the quantum system. The electron has both wave and particle properties, but whether we see wave behavior or particle behavior depends on how we choose to observe it. Albert Einstein found this deeply troubling. He believed that physical reality should exist in a definite state independent of observation, and that our observations should merely reveal what was already there. We had many long discussions about this. Einstein would propose thought experiments designed to show that quantum mechanics led to absurdities if observation really changed the phenomenon. I would respond that the absurdities arose from imposing inappropriate classical concepts onto quantum systems. One of Einstein's cleverest arguments came in the EPR paper of 1935, written with Podolsky and Rosen. They considered two particles that interact and then separate to great distances. Quantum mechanics says these particles can be in an entangled state where their properties are correlated even though neither particle individually has definite properties. If we measure the position of particle A, we can instantly deduce the position of particle B without directly interacting with it. If instead we measure the momentum of particle A, we can deduce the momentum of particle B. Einstein argued that since we can choose to measure either position or momentum of particle A, and our choice determines what property we can know about the distant particle B must have had both definite position and definite momentum all along, waiting to be revealed. Otherwise, our choice about what to measure on particle A would somehow instantly affect the distant particle B, which Einstein thought was absurd. I responded that Einstein was assuming particles have definite properties independent of measurement, but this is exactly what quantum mechanics denies. Before any measurement, particle B does not have a definite position or definite momentum. It is in a superposition. When we measure particle A, we are not just revealing pre-existing properties of particle B. We are determining which aspect of the entangled state becomes definite. If we measure position, both particles collapse to states with definite position. If we measure momentum, both collapse to states with definite momentum. The observation changes the phenomenon for both particles simultaneously because they share a quantum state. Einstein never accepted this. But decades later, John Bell developed a mathematical test that could distinguish between Einstein's view, where properties exist independently of observation, and the quantum view, where observation changes the phenomenon. Experiments testing Bell's inequalities have been performed many times with increasing precision, and they consistently confirm the quantum predictions. Observation really does change the phenomenon. The properties we observe are not pre-existing features revealed by measurement, but are brought into definite existence by the measurement process itself. Now, I want to be very careful about how we understand this. When I say observation changes the phenomenon, I am not saying that consciousness causes changes in physical reality. I am not saying that the universe depends on human minds for its existence. These misinterpretations have caused endless confusion and have made quantum mechanics seem more mystical than it really is. What I am saying is that observation is a physical interaction that entangles a quantum system with a macroscopic measuring apparatus, and this interaction necessarily transforms quantum superpositions into definite classical outcomes. The key is interaction, not consciousness. A photographic plate records the position of an electron whether or not any human ever looks at the photograph. A Geiger counter clicks when it detects radiation whether or not anyone is listening. These are observations in the physical sense because they create permanent records that can later be read and verified. The phenomenon changes when this interaction occurs, when the quantum system becomes entangled with the macroscopic apparatus in an irreversible way. Before the interaction, the quantum system is described by a wave function in superposition. After the interaction, there is a definite classical record. The change happens at the moment of interaction, not at the moment when some conscious being becomes aware of the result. But there is something subtle here that requires careful thought. The measuring apparatus itself is made of atoms and electrons, which are quantum objects. So why do we describe it classically? Where is the boundary between the quantum system that is in superposition and the classical apparatus that records definite outcomes? This is the measurement problem, and it is one of the deepest questions in quantum mechanics. My answer, developed through many years of reflection and discussion, is that we must maintain this quantum classical distinction as a fundamental feature of how we do physics. We need classical concepts to describe experimental arrangements and communicate results. The measuring apparatus must be described classically, using ordinary language and definite properties, because that is how we share knowledge and verify claims. But the quantum system being measured cannot be described this way. It requires wave functions and superpositions. The observation, the measurement, is the process that bridges these two domains. It is where quantum indefiniteness becomes classical definiteness, where superposition becomes a single outcome, where potentiality becomes actuality. And this process necessarily changes the phenomenon because the phenomenon before observation is quantum and the phenomenon after observation is classical. Some physicists have found this unsatisfying. They want to eliminate the distinction between quantum and classical, to describe everything, including the measuring apparatus, purely quantum mechanically. But when you try to do this rigorously, you run into profound difficulties. If you describe the measuring apparatus quantum mechanically, then it too should be in a superposition of different measurement outcomes. The combined system of quantum object plus measuring apparatus is in a superposition. But we never observe such superpositions of macroscopic objects. We always see definite outcomes. This is Schrödinger's cat paradox, which Owen proposed to highlight what he saw as the absurdity of quantum mechanics. If a cat is in a box with a quantum device that has a 50% chance of releasing poison, then before we open the box, the system should be in a superposition of cat alive and cat dead. But we never see cats in such superpositions. Opening the box always reveals either a live cat or a dead cat, never a superposition. My response was that the cat and the poison mechanism are part of the measuring apparatus, part of the classical domain. They are already constantly interacting with their environment in ways that destroy quantum coherence. The decoherence from these environmental interactions effectively forces the system into one classical outcome, or another, even before any human opens the box. The observation that changes the phenomenon is not the act of a human opening the box. It is the physical process of quantum decoherence driven by environmental interactions. This concept of decoherence, developed more fully in later decades, helps explain why observation changes the phenomenon. When a quantum system interacts with a macroscopic apparatus or environment with many degrees of freedom, the information about quantum phases gets dispersed into the environment in such a complex way that quantum interference effects are suppressed. What remains are classical probabilities for different outcomes. The phenomenon has changed from quantum to classical through this interaction. But decoherence does not solve the measurement problem completely. It explains why we do not see macroscopic superpositions, but it does not fully explain the transition from many potential outcomes to one actual outcome. It does not tell us why, when we look, we see one specific result rather than remaining in a superposition of having seen all possible results. This is where the measurement problem remains genuinely mysterious, where our understanding has limits. Despite these difficulties, the central insight remains clear and experimentally verified. Observation changes the phenomenon. The phenomenon without observation is a quantum superposition with indefinite properties. The phenomenon with observation is a definite classical outcome. The change is not an illusion or an artifact of crude measurement techniques. It is a fundamental feature of how quantum mechanics works. This has profound implications for how we think about physical reality. In classical physics, we imagine that the world exists in a definite state at all times, whether we observe it or not. Tables and chairs and planets have definite positions and velocities. Our observations reveal these pre-existing properties without fundamentally altering them. But quantum mechanics says this picture is wrong at the atomic level. Electrons and photons do not have all their properties in definite form until observations force them into definite states. Does this mean reality is subjective, dependent on observers? No. The quantum state evolves according to objective laws, the Schrödinger equation when no observation occurs and the collapse rule when observation does occur. Different observers making the same measurement will get consistent results. There is an objective quantum reality, but it is a reality of wave functions and superpositions, not a reality of definite classical properties. The observation changes the phenomenon from quantum reality to classical reality, from indefinite to definite, from potential to actual. And this change is necessary for physics itself. Without observations that yield definite outcomes, we would have no way to test theories, no way to communicate findings, no way to do science at all. The change that observation creates is not a defect or disturbance to be minimized. It is an essential feature of how we gain knowledge about the quantum world. I have spent much of my life trying to help physicists and philosophers understand this. It requires giving up certain intuitions about reality that seem obvious based on everyday experience. It requires accepting that observation is not passive revelation but active participation in creating the phenomena we observe. It requires recognizing that quantum and classical descriptions are both necessary but apply to different aspects of the physical world. Why does observation change the phenomenon? Because phenomena at the quantum level do not exist in definite classical form until observation forces them into such form. Because observation is an interaction between quantum and classical domains that transforms one into the other. Because the act of creating a definite record necessarily collapses superpositions into single outcomes. Because the properties we observe are not pre-existing features waiting to be revealed but are brought into definite existence by the measurement process. This is not mysticism. This is physics, grounded in rigorous mathematics and confirmed by countless experiments. It is strange and counterintuitive, yes, but it is how nature actually works at the atomic scale. Learning to accept this, to think in quantum terms rather than classical terms, to recognize that observation changes the phenomenon not through some magical influence, but through the fundamental nature of quantum measurement, this is essential for truly understanding quantum mechanics. The phenomenon is different when we observe than when we do not observe because observation is not merely looking at something that exists independently. Observation is an interaction that transforms quantum indefiniteness into classical definiteness, superposition into single outcome, wave into particle or vice versa depending on what we choose to observe. The observer and the observed are not separate in quantum mechanics. They are entangled through the process of measurement, and this entanglement is what changes the phenomenon from its quantum character before observation to its classical character after observation. This is one of the deepest insights that quantum mechanics has given us about the nature of physical reality, and it has taken nearly a century for physicists to fully appreciate its implications. Observation changes the phenomenon because the quantum world and the classical world are not the same, and observation is the bridge between them, the process that brings definite classical facts out of quantum possibilities. Understanding this is understanding the heart of quantum mechanics itself.